Section 2.4, Measures of Variation. One of the things we look at in statistics is when we have a group of data, we want to see what the differences are among the whole group. We may look at a mean or the average, but we want to see how much each individual varies from that average. For example, suppose I have some basketball players here, and I want to know what the average height is. I got the average height as well as the average weight. And I sort it from highest to lowest. But the first thing I want to find before I do anything else, I want to find the range. The range is the distance from the highest to the lowest. And as I've said before, we want to make sure we are sorting. My highest is, in the height, is 79. I'm underlining that. My lowest is 68. 79 minus 68 is 11. So the range for the height is 11. Range for the weight, my highest is 225. My lowest is 162. 225 minus 162 is 63. So the range for the weight is 63. Now the deviation, we're going to talk a lot about this and use this as a central component for statistics, is the difference between each individual measurement and our mean. For example, I have 10 sets of data here, and this could be salaries of 10 people in thousands. So the first one's 41,000, second one's 28,000. When I add all these up, these 10 individual salaries, I get 415,000. The mean, 415 divided by 10 is 41.5. Now what I need to do is I need to find an individual calculation of each deviation for each individual one. And what I'm going to do is I'm going to take that individual count and subtract 41.5. So in the first case, 41 minus 41.5 is negative 0.5. That's the individual deviation from the mean for the first one. Second one is 38 minus 41.5, which is negative 3.5. And I go through all these, and these are the individual deviations from the mean. All I've done is found the difference between each individual salary and the mean salary. Now the variance is the average of those individual deviations squared and then summarized up. We can't do much with the variation by itself, but it is a tool to get us to where we need to go. So what we have here basically is to find the population variance. Again, that's the sigma squared. That little symbol is sigma. Little o, halfway down the page, squared. And what that is that equals the big sigma. That's what that looks like backwards E is. And do not be afraid of this formula. All that's saying is that x minus u, that is the mean, that is the individual component, minus the mean, x minus u, squared. And then we sum those all up. That's what the sigma means, divide by the number of samples. And we're going to go through this in a second. Now, here's our salaries, as we talked about before. We found the mean, and we've already done this actually 2 pages ago. I add the individual salaries, which is when I add them all up, I get 415 divided by 10, 41.5. I then find the individual deviation, subtracting the mean from each individual measurement. And there's my deviation on the right, negative 0.5 for the first one, negative 3.5 for the second one. Now, here's where the calculation comes in. And again, it's not that difficult. I'm going to square the deviation. Negative 0.5 times negative 0.5, which is deviation squared, is 0.25. Negative 3.5 times negative 3.5 is 12.25. So even if I have negatives here, because it's being squared, it ends up being positive. So there's my deviation squared on the very right. That is that sigma times x minus u squared. add up that deviation squared, all those individual 0.25 plus 12.25 plus 6.25. When I add those all up, I get 88.5. That is the sum of the squares. Then, here's my formula from before. If you look at this, divide by number of samples. 88.5 divided by 10, which is 8.85. I take the square root of that. 8.85 is close to 9, so it is about 3. So my mean salary, when I do all this calculation, is 41.5. We did that earlier. And that means, and remember, that's 41.5 thousand. That means the variation is 3, or about 3,000. Now, that is the formula for the population variance. The sample variance is very similar with the exception of one thing. Instead of the number of samples, my n, it's going to be n minus 1. This is done because the smaller the sample size, the greater the variation. So by subtracting that, we're recognizing the greater variability. But other than that, it is all the same calculation. Sum of the sample minus each individual squared, divide by number of samples minus 1, the square root of all that. Let's go through this again. Talking about concussions, common in many contact sports now, and this is the number of days it would take to recover. We've got a sample of 12 individuals who got concussions. Person 1 took 4 days to recover, person 2 took 7 days, and so on and so forth. It adds up to 90 days. So my mean is my total of 90 days divided by 12. The average number of days for concussion, 7.5 days for recovery. I find a deviation for each individual. First one's 4 minus 7.5. That's my individual minus my mean. Second one, 7 minus 7.5. And you did the calculation on the right. 4 minus 7.5 for the first one is negative 3.5. 7 minus 7.5 is negative 0.5. Then go to the next step. We square each individual numbers of those. Negative 3.5 for the first one. Negative 3.5 times negative 3.5. Which is 3.5, negative 3.5 squared, which is 12.25, as I did before. I sum all those deviations squared up, which is 39. I then take that 39, but instead of dividing by 12, remember, this is a sample deviation, so it's 12 minus 1, n minus 1. So it's 39 divided by 11, which is 3.55. The square root of 3.55 is 1.89, or about 1.9. So the sample deviation for that group of concussions is 1.9 days. And when I look at this, if it's normally distributed, I've got a mean of 7.5 days, which is what we calculated. One deviation, how much the variation is plus 1.9 days, 7.5 plus 1.9, as I'm showing you at the bottom, which is 9.4. Two deviations is 7.5 plus 1.9 plus 1.9, which is 11.3. Three deviations, 7.5, is 1.9 plus 1.9 plus 1.9, or 13.2. Same way in the opposite directions, except I'm subtracting. 7.5 minus 1.5, 1.9 is 5.6. That's minus one deviation. 7.5 minus 1.9 minus 1.9, that's minus 2 deviations, 3.7. And minus 3 deviations, 7.5 minus 1.9 minus 1.9 minus 1.9 is 1.8. So, basically what we're saying here, between minus 3 deviations and plus 3 deviations, the recovery is 1.8 to 13.2 days. That is the variation of each individual measurement to the mean. Now, when we look at these, what we're looking at here for normal standard deviation for a normal distribution, in other words, normally distributed, is from the mean to plus one deviation is 34.13%. From the mean to minus one deviation is 0.13%. So in other words, 68% falls from -1 to +1 deviation. In other words, if I have 1,000 concussions I'm measuring, 680 of them will fall between -1 deviation or +1 deviation. And that I'd recognize that as, based on this deviation, if I have 1,000 concussions, 68% of all the individuals, or 680, will cover between 5.6 and 9.4 days. Same thing as -2 +2 deviations. 13.59% fall between -2 and -1 deviation, and from +1 to +2 deviation, 13.59%. And then 2.14% fall from 2 to 3 deviations, and then -2 to -3 deviations, 2.14%. In fact, if I add up, like I said, 68% fall between -1 and +1 deviation. If I add up from -2 to +2 deviations, 13.59 plus 34.13 plus 34.13 plus 13.59, that's 95%. So 95% fall between -2 and +2 deviations. And then if I add that to 2.14 from -2 to -3 deviations, and 2.14 from +2 to +3 deviations, 99.7% of all the concussions, or 997,000, would fall between -3 deviations and +3 deviations, or from 1.8 days to 13.2 days for recovery. And that's what I've shown you right here. 68% go between -1 and +1 deviation of all the data, 95% fall between -2 and +2 deviations, and 99.7 falls between + or -3 deviations. This is known as the empirical rule, 68, 95, 99.7. And this basically says this is how a normal distribution is seen and recognized. Now, one of the things we can look at to see how much variation there is the coefficient of variation. And this is a simple measurement, it's basically a fraction, population standard deviation divided by population mean. The sample deviation is very similar. Sample standard deviation divided by sample mean. We were looking at our weight and height of basketball players before. We did our calculations, if you remember. We found a mean height of 72.8 inches for all these individuals, and we did a standard deviation of 3.3 inches. We did our calculation. 3.3 divided by 70.8 times 100 is 4.5%. Then we did the weight, 187.8 pounds when I find the weights, the average of all the weights of these basketball players. The deviation, 17.7 pounds. So I divide my deviation, my sample deviation by my sample mean. 17.7 divided by 187.8 times 100 is 9.4%. And you can see the variation is greater in the weight, 9.4%, than the height, which is 4.5%.